Okay, in the previous class, we discussed classification tree, right? And today, and actually on Monday, we're going to do the same thing. Keep going with the classification tree. So let me quickly remind you what we were doing. So go ahead and start jump. Okay? Titanic example, which we discussed in the previous class, right? So I'm going to really quickly remind you what did we do and how we did that. Okay, so in Titanic example, which we looked at before, actually, you have very few handful of variables, right? So the variable that we're targeting is survived, right? Yes or no. So for each passenger, we have the value of this variable. So it's a categorical variable, right? And we're trying to predict a person who will survive and who will die on Titanic based on 3 predictors. And all of our predictors are also categorical variables, right? So therefore, we can build a classification tree. So here's how we did that. We said, go to Analyze menu and go through Predictive Modeling, Partition. Okay. And we have to specify for jump which variable is our target. What's our dependent variable? That would be survived. So I place that into the Y area, right? And what are we using as predictors? So that would be class that the person is traveling, age, and gender, right? So we place them all into the X area. And when I click OK, it gives us the starting point for the tree, right? So right now what we have is only this node that says you have 20 to 100 observations, and actually in order to have more visibility, we have to go to red triangle menu and display options, show split count. Shows actually more than just a split count, it shows also the probabilities, right? So right now I see that 32.3% of people actually survived and 67.7% of people drowned, right, on Titanic. Okay. So it's a mixture. It's not a 50-50 split, so it's not that bad to begin with, but still I have to build a classifier, right? So in the candidates, if I look in the candidates, I can see that the best split of this data can happen based on the gender sex, right? Based on the variable sex. Okay, so why is that? Because log worth is the highest. So the jump software looks at the certain measure. I'm not going to go into the details of how that is calculated, but the higher log worth, the better, the variable as a potential candidate for splitting, right? So that's our first split. And if we click on the split button, then it says, yep, male versus female. So after that, if I look at the candidates, right, the females are best split based on the class, right, that they were traveling. So I have log worth 30.4, and as far as the males are concerned, the best split is right here based on age. So the highest is 30.4, and if I click on the split again, it splits females, right? And basically I can keep going up until there is no more split. There is no more feasible split that improves the predictive performance of our model, right? So if I just keep clicking on the split button, it keeps splitting some of the nodes, right? But at some point in time, and you can see that the tree is getting bigger and bigger and bigger, but at some point in time it stops. So that means that this is it. I built model that under the current settings is not splittable anymore. Well, I mean, we have only 3 independent variables, right? There is only so much splitting that can go, right? You can split on gender variable, which we did, and then after that, age, male, female, child versus adult, right? That's another split. And then you have class is another variable, and there are only like 4 possible splits, right? First class, second, third, and crew, right? That's it. After you did all your splitting, you can't split anymore, really. So we reached the end of the line, right? And one thing that we're going to actually use a lot is how good of the predictive model do we have? So we have to, I mean, this is a classification model, right? And actually what I can do is look at the rules of this classification tree. So if I go to the red triangle menu, Okay, let's see, where is that leaf report, right? Yeah, leaf report. So essentially, that's a summary for me. That's my summary. Okay, different paths how to arrive to the final terminal nodes, and we discussed that this is our starting node, right? And if I have a node that is the result of the split, but it splits further, that's internal node. It's not a final, right? But if I arrive to the final node, final leaf, terminal leaf, that's it. There is no more splitting, and that's basically the set of rules. There is a set of rules that I have to follow that leads along the tree to that specific leaf, right? So for example, this one, right? It's the split based on, first one is sex female, right? Class first, second, and crew, and then after that class first, okay? And that corresponds to the probability of yes, 0.97. All right, do you see that one somewhere here? It's a probability of yes, right? 0.97. Sex female and class first. So that one probably, right? There is an adjusted probability, 0.9686. Yeah, this one right there, right? So essentially, how to arrive to this leaf is you start at the top, then sex female, first, second, and crew, but then you filter out first, so it's first only, right? First class only. Okay. And what we discussed is some of these leaves are pure, right? Can you see any pure? Yeah, this one right here that's a pure subset, right? It has 13 observations, and all of them are yeses, right? So all of these people who ended up in that specific final terminal node, they all survived. So the mixture is as perfect as it can get, right? All yeses, 0 no's, right? If it was other way around, all no's, 0 yeses, that would be also a perfect set, right? But if you look across all these terminal leaves, you will notice that actually it's very rare, right? Most of our terminal nodes, they're a mixture, right? So this one, for example, right there, okay, contains females traveling first class, right? Mostly they survived. So out of 145 people who ended up in this leaf, what we have, 141 survived and 4 of them drowned. So it's actually very good, right? But still it's not pure, right? And some others are even worse, right? Here, for example, okay, this leaf contains 53% of people who drowned versus 46% of people who survived. So it's almost like 50-50 split, right? It's pretty bad mixture. But what we need for our decision-making purposes, this model will be used later for the decision-making purposes, right? If I take any non-classified data point, meaning that I don't know if this passenger drowned or survived, right? So let's say I have such passenger. Okay, then in order for me to predict whether or not it's going to be a survivor or the person who drowned, I need to be able to, first of all, track this person down the tree, right? So making these, movements, right? Is it male or female? Go right or go left? And then I arrive to the final node. I have to be able to make a determination. Will that person have drowned or will that person have survived? Okay. So in other words, even if I have a mixture of the results in the terminal nodes, I have to make a decision. Does that node contain people who I classify as survivors, or is that the node that contains people who I classify as non-survivors, right? And this, so in order for me to do that, I have to compare these probabilities of survival versus non-survival to a specific predefined cutoff probability, right? And we discussed that in the previous class. What's the default cutoff for the classification trees? 0.5, right? So the probability higher than 0.5 is how I classify the observation that ended up in that specific node, right? So in my case, like this one, for example, it's very close to 50-50, right? But still, the scale slightly tipped towards people who did not survive, right? No, 53% versus yes, 46%. So if I have any observation that I didn't classify and I want to assign yes or no to them, and it ended up in this node right here, then I would classify that as a no non-survivor, right? Because probability of no is higher than my cutoff value, okay? That's basically how, but at the same time, you can see that in approximately half of the cases I would be right, right? They would not survive. But in other, like 46% of the cases, I would be making a mistake, right? So therefore, my model doesn't work perfectly. So therefore, there is a performance measure that's called misclassification rate, right? So how do we find it? Very easy, right? Go to the red triangle and say, show fit details, right? Click. Okay. And there it is. It's a confusion matrix, right? So confusion matrix, as you can see, has 4 numbers in it, right? We discussed that in class, I'm just reminding you. Because today, hopefully, if time permits, we're going to actually discuss more performance characteristics, okay? There is a number of observations that I correctly classified, right? So, for example, in this specific data set, 1470 observations I classified as non-survivals, right? And there were actually non-survivors. So that is where the model works fine, right? They didn't survive, and I predicted they wouldn't survive. So that's what's supposed to happen. 270, same thing, right? I classified them as survivors, and they did, in fact, survive. That's model working correctly. 20 people, I predicted that they would survive, but in actuality, they drowned. That's an error, right? And 441 people, I classified as non-survivors, but they actually did survive. So that's another type of error, right? You can think of them as in statistics. We probably discussed type 1, type 2 error, right? When we test hypothesis, remember? Guilty versus innocent, right? We start with innocent hypothesis, but if we reject that, if the null hypothesis is true, the person was innocent, but if we reject that and claim that the person is guilty, that's type 1 error, right? We're rejecting true null hypothesis, right? Other way around, if the person is guilty, so therefore alternative is true, but we conclude that he's not guilty, so we find in favor of null, that means that we are not rejecting the false null hypothesis, right? Which is type 2 error. So it's pretty much same thing, right? These are called false positives, and these are called false negatives, pretty much, right? So I classify them as yes, while in actuality that was a no, false positive, and other way around, right? I classified as a no, while in actuality that was a yes. Okay? All right, so one measure of the predictive power, let me take it back. I'm not measuring the predictive power of the model right now. I'm measuring how nicely my model fits the existing data, right? That's all. There is a difference between how nicely the model fits the data and how nicely it can perform on the unseen data before, okay? So how nicely model fits the existing known data is the goodness of fit, and that's what I have, okay? So fit details, one of the most popular, hands down, performance measures for the classification type of problems, such as this one, classification tree, okay? Misclassification rate. So out of 2,201 observations, I classified incorrectly 20, right? I said yes when they were no's, actually. And 441, I said no when they were actually yeses, okay? So therefore, if you add them together for 61 divided by 2,200, you will get that number, okay? So my model misclassified, that's what it says, approximately 21% of the observations, right? 20.95%. So that's the performance measure. Now, unfortunately, and I believe I mentioned that in the previous class, there is no way to tell is it good or is it bad. Now, of course, what's the ideal thing? What do I want the misclassification rate to be ideally? 0, right? Perfectly classifies yes as yes, no as no, right? And nothing is off diagonal, right? So that would be a perfect scenario. Realistically, that's never going to happen, right? I will never build such a beautiful model that gives me a perfect yes or no, okay? So therefore, there is always going to be some misclassification, realistically speaking, okay? But what's kind of bad about misclassification rate, and I probably shouldn't say bad, it's not bad or good, let's not think about that as in terms of black and white kind of, right? There is no predefined, preset cutoff value, such as, for example, 30%. If the misclassification rate is higher than 30%, then it's a bad model. It classifies over 30% of observations. No, there is no such thing. You want it to be as little as possible. But there are no different gradations of the gray, so to speak, right? Is it a good model? Is it a bad model? It's all actually discussed in comparison, right? So I can take the same problem and apply a different technique, which we are going to learn actually in this class later during this semester, such as, for example, logistic regression, okay? Completely different way to classify, to do the same thing really. Classify observations into 0, 1, yes, no, survive, drown category, okay? And I can run different model against the same data set. Different model will give me also a misclassification rate. Now, if I have multiple models going on, I can take misclassification rates at all of them and compare them against each other, right? And the one that gives me the best predictive performance, lowest misclassification rate, is the one that probably I'm going to pick, right? So this is not that valuable in and of itself, by itself, as it is valuable for model comparisons to pick the best one, okay? There is more than one way to predict who will survive and who will drown. That's just one way to do so, okay? That's pretty much what we did in the previous class. No. So what I want to illustrate next is, tell me, ladies and gentlemen, what was the type of my predictors and the target variables? All of them were categorical, right? So my predictors, class, age, and sex were categorical. Nominal, right? And my survived was categorical, which is why, by the way, I used classification tree in the first place, right? It classifies observations into class 1 or class 2, right? So when I'm using classification tree, I must have the target as a categorical variable. That's a given. But my predictors do not have to be categorical. Let me illustrate it with example. So let's close that file out, okay? And let's go to Scholar. And over there I uploaded the file called Riding Mowers. Okay? Download the file. And it's a very small file as well. I told you that we're going to be doing small data in this class, right? So the words big data I'm going to be purposefully avoiding because the techniques and models that we're going to be discussing in this class, they equally apply to big data or small data. It's the same exact principle. Difference is that when you're dealing with big data, data set is very huge, right? Very big. You have to do some technical, jumping through the hoops to make it happen, right? So to speak. Okay, so let's go ahead and open up the file Riding Mowers. So Riding Mowers is about lawn mowers, as you probably guessed, right? So there are people who buy lawn mowers, and there are people who don't buy lawn mowers, right? So that type of analysis makes sense for companies like Home Depot, right? Lowe's, who sell tools, gardening equipment, etc., right? So who are our primary target customers, right? So in this file, you can see that they collected 24 peeps, right? Half of them, 12, they are owners, so they bought the lawnmower, right? And half of them, another 12, are non-owners. So our target variable, can you guess? What's my target variable in this case? Ownership, right? I want to be able to predict who will potentially buy a lawnmower and who will likely not buy the lawnmower, right? And I'm doing that based on two things, right? My predictors are income and how large of the land do they own. That makes sense, right? Like, for example, I live in the townhouse, right? Virtually no loan. Do I need a lawnmower? No, right? If somebody has, like our professor, Ronnie Cohen, right? She lives in a huge house on a big plot of land. She has her own farm. She probably needs a lawnmower, I'm guessing, right? Yeah. So lot size and also income, right? If I'm low-income person, I probably maybe not going to buy it, right? Because lawnmowers are not cheap, okay? So what can you say about predictors? The predictors are continuous, right? But still, I should be able to build a classification tree that has the same structure, right? It starts with the entire set, all 24 observations, super small data, right? Not just small, it's a super small, okay? And then it basically branches out of that and creates the final terminal nodes, which will tell me eventually whether or not these, people in the terminal node are owners or non-owners. Let's do it, right? So software should handle that no problem. The only question is, of course, in the previous example, when we classified survivors versus non-survivors, the split was easy, right? Male, female, that's it, right? There's nothing else there. How exactly do I split this one? Because let's take a look at incomes, right? What's the lowest income in my set? I see 33. Anybody see something less? 33, right? What's the highest income in my set? Looks like 110, right? Yeah. And no incomes, well, there is one, 51, right? It repeats twice, right? But everything else, all incomes are different, right? How exactly I'm going to make a first split? That's a problem, right? Here's how the software does that, okay? When it deals with continuous random variable, continuous predictor, it tries every single possible split. So every single different value in the range of different incomes, it will try to split the set salaries above that value versus salaries below that value. And it will pick the one that does the best, right? All right. So let's go ahead and do that. I'm going to go into the Analyze menu, Predictive Modeling, Partition, because remember this method not only called classification tree, but it's also called recursive partitioning, right? Because I split the set and I split the resulting sets and I keep going until I'm done, right? So it kind of happens recursively. Okay, so ownership is my Y variable, that's my target. Income and lot size are my axes. These are my predictors, right? Yeah. So same set of steps technically, right, that I'm doing. So I'm clicking OK, and then it says, yep, here is your starting point. So let's actually show the same thing, right? Go to the red triangle, say display options, show the split count and probabilities. Okay, let me supersize it, right? Okay, so split. Isn't it annoying when I have to click on the splitting, right? It would be better if we could avoid this thing, right? And actually, with God willing, we're going to have time to discuss this thing today, okay? I can automate this procedure. But in this, for that, I have to split my data set into something called training and validation set. Really important concept, which we're going to discuss next, okay? So I'm kind of gradually pushing you towards this point, okay? So let's keep splitting this thing. And prune, what does the prune do? It cuts the tree back, right? So instead of growing the tree, making more splits and more leaves, when I click on the prune, it eliminates some of the splits, right? So it's cutting tree back, okay? But I don't want to do that right now. I want to keep splitting. And it looks like I can't split anymore, right? I click split, but nothing happens. So what do we see? Well, we see that the most important income is what? Yeah, for the ownership. To predict the ownership, the most important variable is what? Income, right? Because that's the first split, right? When the tree does the first split, that's your most predictive variable, right? That's the strongest predictor. So therefore, in order to predict if the person is going to own a lawn mower or not, apparently, and the value that is critical that gives us the most pure subset was determined by the software to be 85.5. Look at that. This set is pure, right? Everything above 85.5. Now that makes sense, right? People make a lot of money. They're likely to buy lawn mower because they have spare income, right? Spare money around. Okay. But income less than 85, you can see that, there are questions, right? So 19 people were classified in this area and 62.5% of them, they don't have a lawnmower, and 37.5% of them do have a lawnmower. You know what? The tree is not deep enough, in my view, okay? Can you guess why the tree stopped right there and didn't go any further? Because this one, for example, A, can be split probably further, right? 5.0 is pretty good. 5.1 is also pretty good. This one probably can be split further, but it doesn't, right? Remember we discussed that. There is a limiting factor, minimum split size, right? We discussed that. It's kind of artificial, not so much artificial actually, but by default the minimum split size is 5, right? If resulting subsets are going to be smaller than 5, not going to split, right? And we can change the default. So go to the red triangle and go to the minimum split size right there, okay? And you can see 5, right? So that's why this subset of 8 could not be split further, because no matter how I slice it, one of them is going to be less than 5, right? So that's why this subset doesn't go any further. So let me go ahead and make a 1, just for the heck of it. Let's see what happens, okay? And then I click OK button, and if I start clicking again on the split, the tree actually goes even deeper, right? There are a few more splits until I don't have any splits anymore. Okay, so now let's take a look. This is a pure set, agree? 5 people, all of them are owners, fine. That is a pure set. 1 person, no. So, hold on, 5 people, right? 5 people, all of them are owners, right? By the way, these 5 people, they have lower than 85.5 income, but why do you think they own? Big yard, right? Even though income maybe not so huge, right? But big yard, need cutting grass, right? So therefore they bought it, right? Okay, so this one is also pure, this one is pure. Now, what I wanted to show you is this one right here, okay? I believe. Yeah, this one right here. That's what I wanted to show you. Very important concept in the entire data analytics, in the entire data mining area is overfitting. When I say the word overfitting, what do you hear? What do you think it means? Overfitting. It actually means that building too good of a model, okay, that fits the data too closely. You would say, what do you mean? Are you crazy? That's a good thing, right? If my model follows the data closely, that's perfect, right? That's great. Not necessarily. Here is the deal, okay? Let me illustrate that. Look at these two terminal leaves. Each one of them contains what? Well, this is 1 person and these are 2 people, right? Now let's kind of trace it from the top, right? These are people with income less than 85.5. Fine. But lot size is large enough, right? Lot size is higher than 20, okay? But all of these people have income, there are 3 of them, right? Income less than $61.5 thousand a year, right? So now look at that. One of them had the lot size, or hold on, is that the one that I wanted to show you? Yeah, probably. Hold on, give me a sec. Lot size greater than 20. There were a couple of observations that were actually on the lot, based on the lot size, but yeah, I can't see them right now. I saw them yesterday. Well, let's take a look at these couple of guys, right? So here, lot size is less than 22. There are no owners, right? And here, lot size is greater than 22. They're owners. Okay, so what I'm trying to say is, I guess, sometimes the rules are becoming very, it looks like we're splitting hairs, okay? So it looks like, for example, lot size is greater than 20, but less than 22, then people are not buying lawn mowers. But if it's greater than 22, then they're buying lawn mowers. So the more data you have, in order to, the tree will go very deep, okay, if you allow it to go very deep. In other words, every single nook and cranny that you can find, every single pattern that you will be able to find in your data, the tree will fit. Right now, for example, I have my split size equal to 1. That means that minimal split size, right? That means that if I want to go down to the very last level of observation, that will happen, right? If the tree needs to be built on the level of 1 observation per leaf, that will happen. And there are examples, right here. 1 observation only per leaf, right? And that's a pure set. Well, it's pure. It has to be pure set, right? 1 observation per leaf. It's one or the other, right? It's yes or no. Owns the lawnmower or doesn't own the lawnmower. In other words, that tree, if I go deep enough with the tree, if I have enough levels of splits, I will fit my data perfectly, right? But here is the downside, ladies and gentlemen, okay? Do I want really to fit my data perfectly? No. The reason is, in this data set, there is such thing as noise. Every data set contains noise. In other words, things that are just random, okay? Can it happen? I'm asking you, can it happen that a guy with low income and low yard will buy a lawnmower anyway? It can, right? Because people make the buying decisions only partially based on rational considerations, right? Acting rationally, okay? Sometimes people say, well, I just like lawnmowers, okay? Some people like paintball. Some people like driving muscle cars. I like lawnmowers. I don't care if I make little money, right? I don't care if I have small lot. I just like the feeling, getting out there on Sunday and riding this thing on my yard and, talking with neighbors, Heidi Ho neighbor. You seen that one? Heidi Ho neighbor, right? Wilson. Yeah. So people may buy the lawnmower in spite of all these rules that we're building, right? According to our tree, people with a low income and small yard shouldn't have a lawnmower, but it can happen, right? And if I build a hell of a tree, goes very deep, it catches every single variation, right, in my data. People buying lawnmowers of all kinds of incomes and yards, okay? I'm overfitting my data. I'm essentially, what I'm doing at some point in time is I'm capturing the noise, okay? In other words, this data set contains all kinds of people who make rational decisions and people who don't have rational decision making, okay? So all of that will be included, right? But what will happen, and I'm going to have a very detailed, highly sophisticated model with a lot of rules, right? A lot of splitting, okay? But if I take that model and apply it on the new data that I didn't use before, what do you think will happen with accuracy? It will not be very good, right? Because my new data will have its own noise, right? Different from the noise that I had in my data set, okay? But it will use the old noise, so to speak, from the first model, from the first data that I used, right? And we'll try to apply it to a different data, but the noise is different, the patterns are different, right? So if I'm capturing the noise in the data, the randomness, right? I probably don't want to do that, actually. So I want to capture, my model should be good, but not too good, so to speak, okay? It should capture the essential characteristics, essential patterns in the data, and leave the noise out. So therefore, ladies and gentlemen, here comes the important concept, okay? We have, I believe, enough time to cover that, okay? Let's close that one. Okay, let's close the riding lawnmowers. And let's download yet another data set that we're going to use today, which is Universal Bank CT. CT, I have no idea what it stands for. Last semester I was thinking this stands for Connecticut. Apparently not, I don't know. Connecticut, right? How do you say the word Connecticut? Do you pronounce Connecticut or do you say Connecticut? Connecticut? Okay. Yeah, so here is the data set from the bank, right? How many observations? How large is the data size? 5,000 people, right? All of them are customers of the bank. Now, banks, as you know, they make living, they make money by taking money from you and me, right, at low rate and giving them to somebody else, other people and companies at a higher rate, right? So therefore, it's very important for the bank that people, clients of the bank, they get loans, right? Unsolicited loans, for example. That means that if I approach a person who wasn't planning to get a loan, will they consider and accept that loan? Sometimes people apply themselves, sometimes they're offered a loan and then they make up their mind, right? Like, I'm not planning to take a loan out, but if I receive a call that says, hey, 0% in the next 2 years, how about that? I'm like, well, okay, yeah, wasn't planning on that, but why not, right? So unsolicited, that means that people basically apply themselves, right? They're not being pushed, okay? All right, so let's take a look. The target variable is personal loan. And look at that. If I leave the mouse hovering over the variable, it tells me a little bit of the description, right? What does that variable mean? So this one right there says, personal loan, did he or she accept an offer for a personal loan? Okay, so we offered, and they either accepted or not. That is going to be my target variable, ladies and gentlemen. And you can see that the target variable is, what's the type? Nominal, right? Yes or no, so categorical, right? And I'm going to use all kinds of information about customers. Their age, experience, I'm guessing, yeah, experience in years. Income, well, that speaks for itself, right? Zip code, is it possible that some zip code customers are more likely to accept a loan than other zip code customers?
Yeah.
It is possible, right? Probably based on demographics, right, of people, like, is it a rich neighborhood, is it a poor neighborhood? medium income kind of thing, right? But it's possible that zip code can be a factor, so we keep it. Family, what does that mean? Family size, I'm guessing like if it's a single person, it's 1. If they have 3 kids, that's a 5, right? Or something like that, I don't know. CC average spending on the credit card per month in thousands of dollars. Education, as you can see, is also categorical. 1, only undergrad, 2, graduate, and 3, advanced, meaning PhD, doctor, JD, MD, that kind of thing, right? Okay, mortgage, if the bank holds a mortgage taken out by that person already, right? Securities account, do they have a security, like money market account kind of thing, right? CD account, savings essentially, right? Whether or not they're using online banking, and whether or not they're using online a credit card issued by this bank, right? So all this information I'm using. Okay, remember what we discussed about overfitting, right? That if I use the entire data, all 5,000 observations, I can build a hell of a model, right? It's going to be a gigantic tree. But it will capture all the minute, insignificant variations, all the randomness, right? That's out there, okay? And I don't want to avoid. I want to avoid that. So here's what I'm going to do, and this is a regular practice, okay? Let me illustrate that, just like that, okay? So here is my data set right there, my original data set. It's a very standard practice in the field of data analytics to split your data set typically in 3 subsets, okay? So set number 1, we're going to call it training. Training, okay? Training set is used to train the model. In other words, to build the analytical model. In my case, it's going to be decision tree, right? So this is the training grounds. This is what I'm using to build my tree, okay? Then after that, and that's going to be only part of my set, okay? After that, what I'm going to do is try to validate this model on some data that the model didn't see before. So part of my data set is going to be validation set. Validation set, okay? Validation set is kind of an independent verification, okay? I use the training set to build my model, and I'm going to say, here's the model. Let's apply it to the data that the model did not see before. And that will be validation set. So I'm going to see if my model performs nicely on the validation set. If it does, that means that, yep, it's a good model, right? But what happens if I'm overfitting the data, the error will go up, right? If the model is overfitting the data, if it captures too much noise, which is very specific to the training set, I'm going to apply it to a different set, and it will generate me a bunch of misclassification errors, right? Because I captured too much noise. Model is very specific to my training data, okay? And typically, there is a testing set. Testing set. Testing set is like finally, well, you will see actually what that means, okay? Now, we're not going to use testing set a lot, I got to tell you, okay? So we're going to use primarily training set and validation set, okay? When I'm dealing with classification trees, the validation set is used for pruning the tree, okay? And I'll show you exactly what that means. So, let's go back, okay? So that step is kind of important. So therefore, pay attention, ladies and gentlemen, or else. Okay. So I'm going to split my data set of 5,000 observations into the training set and validation set. I'm not going to have a testing set for now, okay? How to do that? Analyze menu, predictive modeling, and can you guess what's next? Make validation column, right? Kaboom. Right there it says, dear sir, you have 5,000 observations, and can you please specify what proportion of these 5,000 observations goes into each set? So by default, they offer me 75 training set, 25 validation, and training 0%. Fine. Now, here is how we all want to get the same tree, right? You and me, right? Because if we use different data, we end up with different trees, obviously. You understand that, right? Different data, different model, right? But we don't want that, right? And we certainly don't want it during the exam time, right? When you submit your exam and I see a different tree and I'm getting angry and your grade suffers and all that, right? So here's what we're going to do. We're going to split it randomly, but fixed randomly, okay? With a certain seed. So, for example, seed is any number. basically generates random numbers after that, okay? But if we use the same seed, you and me, it's going to be same randomness, and it's going to be pick up same data for the training and validation. Well, let's use 100, for example, just for the heck of it, okay? And then, so it's a fixed random split, right? I'm clicking on the fixed random, and look at that. What happened is I created a column that says validation. Now, in my case, I have training. How many trainings do I have? First 6 observations are training, and then another is validation. Do you have the same? You have the same, right? So that means that these 5,000 observations were split, like each one of them was selected randomly to be part of the training set or to be part of the validation set. But because we used the same seed for the fixed random, we ended up with the same training and validation set, you and me, okay? All right, now let's do the tree building exercise, right? So, and it's very easy, right? We did it twice today. Let's do it one more time. Analyze, predictive modeling, and then what? Partition, right? Partition. So what's my, by the way, here is the variable that's called ID, and it's excluded actually. I just wanted to point out. You see that? For now, these variables that have this stop sign, they're excluded, right, from the model. That means that ID is just a number, 1, 2, 3, 4, 5, etc., right? Is it going to predict for me who is going to take a loan or not? No, right? So I excluded things that probably don't make sense, right? And model doesn't want them in the first place. So I'm going to take personal loan, and that's my target, right? And everything else, starting from age all the way down to credit card, but not the validation column, okay? The real variables, the actual variables, right? I'm going to place them in X. Now, what do I do with validation? I place it right here. I'm telling my tool, my jump tool, that this model will be built using what set? Training or validation? In order to build the tree, we use the training set, okay? Now, you can ask, how in the hell do we use the validation set then, right? So we're going to use the subset essentially, right? And this is actually how to see that. It's very easy. So let's click OK, and I'm going to make it larger, all right? Okay. So, how many observations do you see we have in our top level of the tree? That means count. 3,750. Not 5,000, right? Why not? Remember, the set was 5,000 numbers, 5,000 records, right? But right now I'm using only 3,750 for my tree.
Is that because you took out the noise or unnecessary?
No, that's because I split the, remember 75 versus 25? A quarter of my data set I set aside to be validation, right? And the training was only 75%, 3/4. And that's 3/4, okay? So right now, for my tree, I'm going to use only 75% of my data set. That is my training subset. That's I'm using for the building the tree, okay? Now, remember, we discussed that today. It's kind of annoying to click split. When you have training and validation, you can avoid that. You can go ahead and say go, kaboom, all right? And it creates for you the entire enchilada, ladies and gentlemen. This is your tree, okay? All right. Now, look at that. Right there it says that the tree that I'm seeing right now is actually based on 14 splits. Do you see that number of splits? And there is a vertical line, right? Here's what's going to happen, ladies and gentlemen. Let me get back. We still have a little bit of time. This is an important concept. Here's what's going to happen, okay? This is number of splits. Number of splits in my tree. Okay? And here's my misclassification error. Misclassification error. Okay? So, remember we discussed that. The higher the number of splits, the more detailed tree I'm building, the closer it follows the data, the lower is misclassification rate. Agree? So therefore, on my training set, if I build tree with more and more splits, this is what's going to happen. Okay? So this is my training data. But at some point in time, I'm starting to overfit. Okay? I'm following my training set too closely. It captures all the noise that I don't want. Okay? And Jump is using the validation set simultaneously to prune the tree. Okay? So here's what's going to happen on the validation set. The error will go down, but because of overfitting, at some point in time, it'll start rising, okay? I'm using the too good of a model that follows all the noise in my training data on a completely unseen data, and that creates a lot of misclassification errors. Because I'm using things that are noise from the previous set to apply to my new set, and I'm classifying them plain wrong, okay? So obviously we don't want that, right? So jump basically says, okay, let's build the tree to the full size, and now let's cut it back, okay? Let's cut it back to this point where the validation error is minimal, and after that it starts rising. And you actually can see that, that's the last point that I want to make here, split history. It's actually using something that's called R squared. R squared is the higher the better. And you can see that the blue line, which is training, R squared is getting more and more and more. The more splits you have, the higher R squared you're getting, right? That's your training set. But the red one is validation. You can see that, yeah, R squared is getting high, but at some point in time it levels and starts to go down, right? That's because of overfitting, right? You're picking up the noise. So therefore the jump says, I can make 23 splits, but that's actually too much, right? Because I'm picking the noise. So now from 23 splits, let's cut it down to 14, and that's your optimal tree size, okay? And that's essentially how jump builds the classification tree, okay? Any questions? All right.